So the work that I'll talk about today is really a collaboration between theory and experiment. So on the experiment side is my postdoc, Antonio Rossi, and on the theory side is Giacomo Resta, who is a grad student of Sergei Sabrasov at UC Davis. So I hope I'll do Giacomo justice when I present his DFT calculations. The experiments were done at the Advanced Light Source at Berkeley Labs, where Antonio also has a partial appointment, and our samples come from the 2D Crystal Consortium at Penn State. So the experiments were done at the Maestro beamline at the Advanced Light Source, and the M in Maestro stands for microscopy. So this is a beamline that has really been one of the pioneers in taking photoemission techniques into the realm of microscopy. So they have a number of experiments available here, such as LEAM-PEAM, but more relevant to this talk is nano-ARPES and micro-ARPES, which provide, whoops, this slide gets away from me, which provide either a spot size below a micron for nano-ARPES, or a spot size of on the order of several microns or several tens of microns for the micro-ARPES setup. So for the experiments that I'll show you today, we use the micro-ARPES system, and we also used a potassium source that is available there. And I'll discuss in a little bit of detail what this does in case someone is not familiar with this method of surface preparation in ARPES. And we don't actually put a banana in the ultra-high vacuum system. Okay. So potassium dosing is a relatively ubiquitous tuning knob that is available at most, if not all, synchrotron ARPES end stations nowadays. And basically, you dump potassium on the surface of a crystal after it is cleaved. And the most simple thing that it does is it donates electrons to the sample. Sometimes you can also have the displacement field from the positive ions that are left over contributing to the observed spectra. So what potassium dosing does in its most rudimentary implementation is it gives us a little help with one downside of ARPES, which is that only occupied states are observed. So this is something that is well known. We're subjected to the Fermi-Dirac cutoff. We can do a little bit better populating some unoccupied states by raising the temperature. But another way to occupy the initially unoccupied states without raising the temperature is dumping potassium or another alkali metal on the surface. This can add electrons and bring up the chemical potential, exposing states that were previously unoccupied. So usually this is just a technique for shifting the chemical potential a little bit, but occasionally something more interesting does happen. And our motivation for this work was really this idea of looking for new phases via this relatively rudimentary way of in situ materials tuning. So there are a number of examples in the recent literature where people dose potassium and observed something more interesting than just a chemical potential shift. So one example is this electric field tuned topological phase transition in ultra-thin sodium-3 bismuth. So in the ultra-thin regime, sodium-3 bismuth is actually a quantum spin Hall insulator. And these authors claim that with the displacement field that appears when the potassium atoms donate their electrons, you can actually have an electric field tuned topological phase transition. Another example from the 2D materials world is this work, where in tungsten disulfide, there is a band over here, which is split by spin-orbit coupling. And with potassium dosing, they're actually able to enhance this splitting, implying an enhancement of the spin-orbit coupling. And these sorts of techniques have been used quite a bit in the iron-based superconductors, where carrier tuning does play an important role. And there are some surprising results there. For example, this work claiming that the superconducting gap with potassium dosing is actually enhanced beyond what it is in the optimally doped bulk crystal. So you'll notice on this graph that the plot corresponding to the potassium dosing has 40 seconds, 90 seconds, 130 seconds. So that is the tuning knob that we actually have in the experiments. We can control how long we've been depositing potassium on the surface. This is not a good way to determine how many electrons have actually been added, and I'll come back to that in a little bit. Okay, so to have the highest probability of actually getting something more interesting than a chemical potential shift with potassium dosing, it helps to have a material that does a lot of different things. And tungsten ditelluride is one of those multifunctional materials that is characterized by extreme tunability. And this slide is intentionally busy, and I don't expect you to read all of it. I'll discuss the relevant pieces in a little bit, but today I'll be discussing the bulk system, but I'll remind you, if you're not following the 2D materials field, that this material can also be exfoliated down to a monolayer or several layers. And in that regime, it actually becomes a quantum spin Hall insulator, perhaps one of the most robust examples that has been found thus far, and it becomes superconducting with gating. All right, so in the case of bulk tungsten ditelluride, it turns out that many of the emergent phenomena in that material, carrier tuning plays an important role one way or another. So this material first rose to prominence a few years ago because of its large and non-saturating magnetoresistance. So this was attributed to perfect compensation between electron and hole pockets. And there is photoemission support for that, but it's maybe not fully accepted in the community. But anyway, that's the most common explanation for the large and non-saturating magnetoresistance. More recently, this material became prominent as a predicted type 2 Weil semimetal that was tunable by either strain or molybdenum alloying. So a type 2 Weil semimetal is characterized by tilted Weil cones instead of ones that obey Lorentz symmetry. So this prediction has been pursued by many different ARPES groups. I would say from the photoemission side of things, and I can come back to this in the Q&A if people are really curious, the ARPES evidence that it's a type 2 Weil semimetal, the direct evidence is fairly tenuous, and I think it would be almost impossible to confirm in this specific compound. But there are transport signatures that support this prediction, which I can't comment on their veracity because it's not my expertise. But for the transport signatures to be observed, one has to electron dope because the Weil points are actually located approximately 80 millielectron volts above EF. And finally, another exciting result in bulk tungsten ditelluride is the observation of pressure-induced superconductivity, hydrostatic pressure. So in these experiments, it appears that superconductivity only emerges when, first of all, the large and non-saturating magnetoresistance goes away, and also when there's a change in the sign of the Hall number. So clearly, carrier tuning does a multitude of things, and tuning carriers is a reliable method to get new phenomena in tungsten ditelluride. So moving on to the ARPES data, and there's one important complication in the ARPES spectra of this material that actually helps us narrow down the explanation of what we ultimately see with potassium dosing. So it was reported by the Baumberger group a few years ago that this material, it actually has two non-equivalent cleaved surfaces, which we call face A and face B. So if you have one sample, you cleave it, you flip it over, you cleave it, you're gonna get a different spectra. You're gonna get these two different types of spectra. And this is attributed to a very subtle inversion symmetry breaking along the C-axis, where in one tungsten ditelluride block, you have your tungsten layer, and then you have tellurium atoms above and below. And the average tellurium height above and below are actually a little bit different, which leads to the different spectra in different terminations. So let me walk you through these spectra. So first of all, the electron pocket is here, or I should say pockets rather, there's two of them, a little bit further from the gamma point, and then the whole pocket is here, closer to the gamma point. And the characteristic of face A, at least before we add potassium, is that there is a gaping hole right here, a region of no bands. This is in contrast to face B, where you have your electron in your whole pocket, but you have this V-shaped feature that appears between the two of them. So this V-shaped feature has been observed by every ARPES group that measured these materials, and it has been shown to be a surface-like band. So with photon energy, it does not disperse, indicating that it's two-dimensional. So because it is two-dimensional and it looks sort of archy, it was sometimes incorrectly attributed to the Fermi arcs connecting Weil points. So that is not the case actually, because if you actually look where the Weil points are, they're very close together and they are not connected by that surface state. So this large surface state, I don't want to say it's topologically trivial because there are now proposals that it's not topologically irrelevant. So I'll just say that it's not related to the predicted type 2 Weil semimetal. So these are DFT calculations, slab calculations, obviously, because we're interested in surface states. And in all of the calculations I'll show, darker colors indicate a more surface-like band, and lighter colors indicate a more bulk-like band. So these calculations reproduce the fact that one of the faces has these surface states between the electron and the hole-like pockets, and the other one does not. So you guys probably see these states near gamma, and these also show up in the calculations, but it turns out that they're just a little bit below EF, which is why they don't show up in these contours, which are exactly at EF. So with photo emission Fermi surface maps, we have some integration window in energy, which makes us see states that are just a little bit below EF. Okay, so moving on now to the dispersions in energy and momentum. So here they are for face A and face B. So as a corollary of a material that does a lot of different things, you often end up with a rather complicated band structure. But I'll assure you that most of these states over here are bulk states, and they're the same for face A and face B because it's only the surface terminations that are different. So where we do see differences other than the gamma point, which will not be the focus of the discussion today, is here at around kx equals 0.3, where on face A, between the electron and the hole band, we see nothing, whereas on face B, between the electron and the hole band, we see this sort of teardrop shaped feature. Okay, so now we add potassium. We add electrons. And there are changes that happen in both of the faces. And this change occurs for a very small amount of potassium dosing, corresponding to a shift in chemical potential of approximately 30 millielectron volts. So I mentioned earlier that the control knob that we have as an experimentalist is how much time we've been evaporating potassium on the surface. So that is not a good way to surmise how many electrons that you've added, because the way it happens is the first couple of potassium atoms, they usually do donate their electrons, but what that does is it sets up an electric field that opposes further potassium atoms from donating their electrons. So initially, potassium is deposited pretty much all ionized, but as you deposit more and more, it becomes more neutral. So, the amount of charge that's contributed is not a linear function of how much time you've been dumping potassium on the surface. So what we can determine pretty accurately in our experiments is how much the chemical potential has shifted. We do this by lining up the bands as best as we can before and after. And if one wants to make some predictions or hypotheses about how the charges distribute in the top several unit cells, you can connect this to the number of electrons. But what we can rigorously measure is the shift in the chemical potential. Okay, so with that disclaimer out of the way, let me walk you through what we actually see. So on face A, initially, there was a gaping hole between the electron and the hole-like band, and afterwards it has been filled by some states, and exactly the opposite thing is observed on face B. Initially, there were states, and then they are gone. And if you don't believe this image that they're gone, I'll show you a Fermi surface map that maybe shows it a little bit clearer. So interestingly, it also looks like face A and face B have kind of switched. So initially there was nothing on face A, afterwards there's nothing on face B between the electron and hole pockets. And I'll explain a little bit later why this coincidence actually makes sense. Okay, so another way to decompensate electrons and holes in tungsten ditelluride is by raising the temperature. So it was found that this material undergoes a Lifshitz transition at around 160 Kelvin, where the hole pocket vanishes below EF, or rather it doesn't vanish, but it goes below EF. And qualitatively, this looks a lot like adding electrons, but if we actually look at the spectra, and this is from a paper a few years ago, so these are spectra on face A, and I don't know if you can see clearly, but at low temperature, there is nothing between the electron and hole band over here. And then above the Lifshitz transition, it is fuzzy, but there's still not a band there, which would be very clear if it was present. So it looks like there is something different about adding electrons versus decompensating carriers with temperature. Okay. So here's the doping induced change in fermiology. So we have before the potassium doping, we have our gaping hole and we have our V-shaped surface feature. And then after dosing, you have a feature appearing here where there was once a gaping hole, and then you have a gap appearing on face B where there was once this V-shaped surface state. So we can focus a little bit closely on the momentum region where this change is actually happening right here in the green boxes, which are lined up for all the images. And here in the bottom panel, we show the difference plot where where on face A, you have an overall increase in spectral weight in this region, whereas on face B, you have an overall decrease of spectral weight in this region. Okay, so to guide how we think about this observation, let me say a little bit about crystal structure. So tungsten ditelluride is always in the same structural phase at all temperatures, and it's called the gamma phase, also called the TD phase. This is in contrast to a related compound, molybditelluride, which has many of the same emergent bulk phases, but it actually undergoes a structural phase transition where it is this other structural phase at room temperature, and then at low temperature, it goes into the gamma phase. So this other structural phase is called beta, or 1T prime, and it differs from the gamma phase in so the difference can be described in two different ways. So one way to describe it is a 4-degree tilt in the unit cell. Another way to think about it is you have a series of small planar shear displacements of subsequent tungsten ditelluride layers. And it's this language that will be most useful for talking about the theory that I'll show next. So the distinction between these structures is important for a number of reasons. So if you're interested in what topological phase the crystal supports, this is kind of an underlying principle. And there was a prediction a few years ago that this structural phase transition, which does not happen as a function of temperature, can be driven by hole doping. And later on, there was an observation that it can be driven by a terahertz driving field, where the mechanism there is really to drive these small planar shear displacements. So as a disclaimer, I'm not claiming that we're observing this bulk structural phase transition, but we're observing something that at the end of the day ends up looking kind of similar. So I should mention, if one wants to distinguish these bulk structural phases via photo emission, it's very difficult. The bulk bands are actually almost identical. The changes are so minute that I don't think they could be experimentally resolved. But it turns out that the surface states on these different structural phases on the two non-equivalent phases are doing very different things. Okay. So we want to think of this structural phase transition as a shear displacement. And these calculations show the configurational energy with various shear displacements of one layer. And this calculation is for the bulk. So without doping, which is the orange, the gamma phase is the minimum, no surprise there. With hole doping, it actually reduces repulsion between adjacent tellurium antibonding orbitals. So the minimum energy is at a shear displacement of 0.3, which does correspond to the beta phase. And with electron doping, which is the green and the red, the global minimum of the energy moves to a small negative shear displacement, but still pretty much the gamma phase. But then there is a local minimum that develops at a shear displacement of 0.8 angstrom, which we call the metastable phase. And here is the same thing, but for a slab geometry, where the qualitative observations are exactly the same, but quantitatively, the difference between the energy of the metastable and the global minimum with electron doping becomes much reduced. So it should be noted that it's difficult to distinguish these energy differences of 1 or 2 millielectron volts in this material because of the difficulty in modeling the van der Waals interactions. So it is possible that in reality, the metastable phase is the global minimum, or it's also possible that in our experiments, other details such as the displacement field or relaxation near the surface drive this to be the global minimum. And I'm putting this out there because our data are very consistent with this explanation of a shear displacement of 0.8 angstrom. So let me walk you through that. So these are slab calculations showing subsequent shear displacements of one layer. And this is modeling face A. So the experimental observation is before, there's nothing between the electron and hole band. Afterwards, there's something there. So starting with 0 shear displacement, initially there's a band that is above EF, but as the top layer is sheared to the right, you can see this band pushing below EF. And if we have a more fair comparison, blocking the part that ARPES does not see, you can see that the experimental observation of now you don't really see it and now you see it is very much captured by this model of a shear displacement of the top layer. Additionally, the beta structural phase, the surface state that it produces, does also have that same qualitative property in that on one of the faces, there's a surface state that is found below the chemical potential. So doing the same calculation on face B, so that's the one where first you see it and then you don't. This is what is observed. So initially, without any shear displacement, there is a surface-like band that is below the Fermi energy. And with successive shear displacements, it gradually gets pushed up. And then finally, if we compare it to an ARPES experiment where we don't see unoccupied states, first you see it, and then you don't see it. And again, the beta structural phase gives qualitative agreement with the experimental observation as well as this metastable phase. So there is this intriguing coincidence, two intriguing coincidences that I pointed out. So one is that with potassium dosing, the different terminations seem to switch. So the spectra that were initially characteristic of face A afterwards become characteristic of face B. The other coincidence is that the spectra qualitatively look an awful lot like the beta phase, which we don't claim to be actually producing because it is energetically unfavorable. But if you compare what the crystal structures, this coincidence starts to make sense. So this is the metastable phase, so 0.8 angstrom shift of the top layer compared to the gamma phase. And the region of qualitative agreement is marked by the green box. So in this case, there's only one layer of qualitative agreement, which makes sense because you shifted the top layer and now and you line it up and now everything below disagrees. The second panel is the metastable phase versus the inverted gamma. So basically the orthorhombic phase, but flipped over so that face A becomes face B. So here, the qualitative agreement extends to the top two layers. And then finally, we have the metastable phase compared to the beta structural phase, and the qualitative agreement is on three layers of tungsten ditelluride. So with this, the qualitative results that first of all, A and B seem to switch, and secondly, that before you have good agreement with the gamma phase, which we should, and then after we have qualitative agreement with the beta phase with respect to which surface states we see and we don't see in an experiment that only measures occupied states, this qualitative statement also agrees with our proposal that with potassium dosing, we're able to induce a shear shift of the top layer. So to conclude, we find that the surface states of tungsten ditelluride are a very sensitive measure of the structural phase because the bulk bands definitely are not. And we also found that a small amount of potassium dosing produces a change in the surface bands that's consistent with a shear displacement of the top unit cell. And then finally, we find that with potassium dosing, the first three layers of the predicted crystal structure that we end up in are consistent with another structural phase that is not realized under ambient conditions. And this is an attractive structural phase because, first of all, in ultra-thin tungsten ditelluride, it's actually in this crystal structure that the quantum spin Hall insulator is seen. And with superconductivity under pressure, this may also be the structural phase that is relevant, although that is still debated. So that's all I have to say, and I'm happy to take questions.
Questions? Are there anything from Andy? Hi. I guess you want to just go up there. Yeah, you go up there and sure.
No. So now just to the world at large, I want to reveal my ignorance. So the first question I just didn't quite get. The shear displacement of the top unit cell, how does that relate to the beta structural phase that you talk about in the next bullet point? I mean, is that the same thing, or are there two different structural things going down in the material?
Yeah, okay. Yeah, thanks for letting me make that more clear. So the shear displacement is the thing that we think is more likely to be happening because it is energetically more favorable. If we take the crystal structure, sorry, let me talk into the mic. If we take the crystal structure with that shear displacement and lay it on top of the beta structural phase, it matches in the top 3 layers. So that's where the qualitative agreement lies.
I see. Great. And then the second question, which was related, was I know you had DFT calculations which sort of suggest this shear. But is there a simple physical mechanism that would let one understand why it wants to do this shear on potassium doping?
I'm not sure exactly. So the calculations of the energies of the configurations, it does show a local minimum. How it gets into that local minimum, I'm not sure. Maybe the displacement field plays a role, but I don't have an answer for that.
Well, I'm sorry, let me just make my question more clear, although I understand that I'm asking a theory question and it's not, but my question was not so much how it gets there, but just what's the reason why that phase, why that local minimum exists on potassium doping? You know, it just, it seems it's counterintuitive that you add charge and it wants to make a shear. And DFT obviously says it wants to do that. The question is just, is there some intuitive understanding of why?
Yeah, so it's related about where it's related to where the doping actually goes in the tellurium orbitals. So with electron doping, they let me go back to that over here. Yeah, so here you can see sort of the different bond angles. So here, which would correspond to the beta phase, you have sort of the tellurium atoms on top of each other, which is very much disfavored with electron doping because the electrons go into those tellurium orbitals. But with this kind of shift where they're angled towards each other, you can avoid that repulsion.
I see. Thank you. Other questions? Okay, so let's move on to the next session and asking again for a very nice talk.